and his name will be Norm Hull, because he's just a normal guy.
The Free Energy Principle, a Unified Brain Theory by Karl Friston. Abstract. A free energy principle has been proposed recently that accounts for action, perception, and learning. This review looks at some key brain theories in the biological, for example, neo-Darwinism, and physical, for example, the information theory and optimal control theory. Sciences from the free energy perspective. Crucially, one key frame that runs through each of these theories: optimization. Furthermore, if we look closely at what is optimized, the same quantity keeps emerging, namely value, expected reward, expected utility, or its complement. Surprise, prediction error, expected cost. This is the quantity that is optimized under the free energy principle, which suggests that several global brain theories might be unified within a free energy network. Despite the wealth of empirical data in neuroscience, there are relatively few global theories about how the brain works. A recent proposed free energy principle for adaptive systems tries to provide a unified account for action, perception, and learning. Although this principle has been portrayed as a unified brain theory, its capacity to unify different perspectives on brain function has yet to be established. This review attempts to place some key theories within the free energy framework. In hope of identifying common themes, I first preview the free energy principle and then deconstruct several global brain theories to show how they all speak to the same underlying idea. The free energy principle. The free energy principle, box 1, says that any self-organizing system that is at equilibrium with its environment must minimize its free energy. The principle is essentially a mathematical formulation of how adaptive systems, that is, biological agents like animals or brains, resist the natural tendency to disorder. What follows is a non-mathematical treatment of the motivation implications of the principle. We will see, although the motivation is quite straightforward, the implications are complicated and diverse. This diversity allows the principle to account for many aspects of brain structure, function, and lends it to potentially unify different perspectives on how the brain works. In subsequent sections, I discuss how the principle can be applied to neuronal systems as viewed from these perspectives. This review starts in a rather abstract and technical way, but then tries to unpack the basics idea in familiar terms. Motivation, resisting a tendency to disorder. The defining characteristic of biological systems is that they maintain their states and form in the face of constantly changing environment. From the point of view of the brain, the environment includes both the external and the internal milieu. This maintenance of order is seen at many levels, distinguishable biological from other self-organizing systems. Indeed, the physiology of biological systems can be reduced almost entirely to their homeostasis. More precisely, the repertoire of psychological and sensory states in which an organism can be limited, and these states define the organism's phenotype. Mathematically, this means that the probability of these interoceptive and extraceptive sensory states must have low entropy. In other words, there is a high probability that the system will be in any small number of states, and a low probability that it will be in the remaining states. Entropy is also the average self-information, or surprise. More formally, it is a negative log probability of an outcome. Here, a fish out of water would be in a surprising state, both emotionally and mathematically. A fish that frequently forsook water would have high entropy. Note that both surprise and entropy depend on the agent. What is surprising for one agent, for example being out of water, may not be surprising for another. Biological agents must therefore minimize the long-term average of surprise to ensure that their sensory entropy remains low. In other words, biological systems somehow manage to violate the fluctuation theorem, which generalizes the second law of thermodynamics. The free energy principle. Part A of the figure shows the dependencies among the quantities that define free energy. These include internal states of the brain and quantities describing its exchange with the environment, sensory signals and their motion, plus action. The environment is described by an equation of motion, which specifies the trajectory of the hidden states. The causes of sensory input comprise hidden states, parameters, and precisions controlling the amplitude of the random fluctuations. Internal brain states and minimize free energy, which is a function of sensory input and probabilistic representation of its causes. This representation is called the recognition density and is encoded by internal states, micro. The free energy depends on two probability densities, the recognition density and one that generates sensory samples and their causes. The latter represents the probabilistic generative model, denoted by the M, the form which is entailed by the agent of the brain. Part B of the figure provides alternative expressions for the free energy to show what its minimization entails. Action can reduce free energy only by increasing accuracy. that is, selectively sampling data that are predicted. Conversely, optimizing brain states makes the representation approximate conditional density in the course of sensory input. This enables action to avoid surprising sensory encounters. A more formal description is provided below. Optimizes sufficient statistics representations. Optimizing the recognition density makes it a posterior or conditional density on the course of sensory data. This can be seen by expressing the free energy as surprise, plus a callback library divergence between the recognition and conditional densities encoded by the internal states in the figure. Because this difference is always positive, minimizing free energy makes the recognition density an approximate posterior probability. This means the agent implicitly infers or represents the causes of its sensory samples in a Bayes optimal fashion. At the same time, the free energy becomes a tight bound on surprise, which is minimized through action. Optimize action. Acting on the environment by minimizing free energy enforces a sampling of sensory data that is consistent with the current representation. This can be seen with the second arrangement of the energy as a mixture of accuracy and complexity. Crucially, action can only affect accuracy encoded by the external states in the figure. This means that the brain will reconfigure sensory epithelia to sample inputs that are predicted by the recognition density. In other words, to minimize prediction error. In short, the long-term distal imperative of maintaining states within physiological bounds translates into short-term proximal avoidance of surprise. Surprise here relates not just to the current state, which cannot be changed, but also to movement from one state to another, which can change. This motion can be complicated and itinerant, wandering provided that it revisits a small set of states called a global random, a tractor, that are compatible with survival. For example, driving a car within a small margin of error. It is this motion that the free energy principle optimizes. So far, all we have said is that biological agents must avoid surprises to ensure that the states remain within physiological bounds. See supplementary information S1. For a more formal argument, but how do they do this? A system cannot know whether its sensations are surprising and could not avoid them even if it did know. This is where free energy comes in. Free energy is the upper bound on surprise, which means that if agents minimize free energy, they implicitly minimize surprise. Crucially, free energy can be evaluated because it is a function of two things to which the agent has access: its sensory states and the recognition density that is encoded by its internal states, for example, neuronal activity and its connection strengths. The recognition density is a probabilistic representation of what caused a particular sensation. This variation of free energy construct was introduced into statistical physics to convert physical probability density integration problems into easier optimization problems. It is an information theoretic quantity, like a surprise, as opposed to a thermodynamic quantity. Variation of free energy has been exploited in machine learning and statistics to solve many inference and solve learning problems. In this setting, surprise is called the negative modded evidence. This means that the minimizing surprise is the same as maximizing sensory evidence for an agent's existence. If we regard the agent as a model of its world in present context, free energy provides the answer to a fundamental question: how do self-organizing adaptive systems avoid surprising states? They can do this by minimizing their free energy, so what does this involve? Implications: actions and perception. Agents can suppress free energy by changing the two things it depends on. They can change sensory input by acting on the world in their internal states. This distinction maps nicely onto action perception. One can see what this means in more detail by considering three mathematically equivalent formulations of free energy. The first formulation expresses free energy as energy minus entropy. This information is important for three reasons. First, it connects the concept of free energy as used in information theory with concepts in statistical thermodynamics. Second, it shows that the free energy can be evaluated by an agent because the energy is the surprise about the joint occurrence of sensations and the perceived causes, whereas entropy is simply that of agent's own recognition density. Third, it shows that their free energy rests on a generative model of the world, which is expressed in terms of possibility of a sensation and its causes occurring together. This means that an agent must have an implicit generative model of how causes conspire to produce sensory data. It is this model that defines both the nature of the agent and the quality of the free energy bound on surprise. The second formulation expresses free energy as supplies as a divergence term. The perceptual divergence is just the difference between the recognition density and the conditional density or posterior density of the causal sensation, given the sensory signals. This conditional density represents the best possible guess about true causes. Difference between the two densities is always non-negative, and free energy is therefore an upper bound on surprise, thus minimizing free energy by changing recognition density.